Cashier.
Yeah. Oh, in ancient Egypt, killing a cat was punishable by death. There's about 100 distinct breeds of domestic cats.
When you teach us okay, then let's get started. So, from today, we are going to talk about advanced manufacturing technology. Advanced manufacturing technology mainly include three aspects. Okay, so this is for us, for me. Maybe some people have some other ideas, but I cannot cover everything here. And we are going to focus on EDM, and we are going to focus on additive manufacturing, and we are going to focus on laser-based machining. Laser-based machining. These are three aspects about advanced manufacturing technology. So this is the EDM, and EDM will be the first topic I'm going to talk about. So this, I'm going to give you some basic ideas on what this is the EDM is about and how it works and what kind of applications the EDM can use. And also, there is no hand calculation. So for this is our final exam. So this one, this will be covered, definitely will be covered. But all the problems that are related to this advanced manufacturing technology and is conceptual. Okay, so there is no worries about the hand calculation. No hand calculation, and you can just sit there or just sit there in person or sit there online. Just listen to my story. This is a history class. Talk about the story. But when I say something is important, for example, EDM, what is the typical system of EDM? And I will ask you guys to pay attention to this one. Maybe in the final, I will say use your own language to describe and to list the components of the EDM system, and you should be able to do that. Okay. And this evening, I'm going to give you some videos. This is the YouTube videos about the EDM. You can take a look about this. Take a look at this is the videos, and to have a better understanding of EDM. Any questions before we get started? No question?
I have an unrelated question. How do you want us to submit the homework? Because it's a little too project to mail, even zipped.
You mean the model, right?
Yeah.
Model, you can share the Google Drive if you want. This is one way. Email is how huge it is.
Yeah, that's not working for me for some reason. I can talk to you about it later. Never mind.
Okay. So here, so this is EDM. Dr. Mohammed Jahan, he is my close friend and is a long-term collaborator. And he is from the Miami University, and we have published many journal articles and conference papers together. So now here he is an EDM expert. So we are going to use this material and to talk about the EDM. And what is EDM? So first you should know that the EDM is standing for the electrical discharge machining. It is one of the earliest non-traditional manufacturing processes. Having an inception 50 years ago, this is about 1950, in a simple die-seeking application. So what is die-seeking? I'm going to talk about it. So nowadays, currently, it is most widely used non-traditional machining process for production of injection molds and dies, the cutting tools and components with complex shapes, and mass production of common objects. So here is the application. You should know that, okay? If I give you this kind of problem, you should know where to find the answers. So EDM is used in large number of industrial areas, and so, for example, automotive industry, electronics, domestic appliance, machines, packaging, and telecommunications, and watches, aeronautic toys, and surgical instruments. The EDM is sometimes EDM is chosen and over this is the traditional one. So here are the the answers. There are many advantages of EDM over the traditional methods. The major advantage is that any material that conducts electricity can be machined. So this is a very, very amazing property. And for the traditional one, if the material is very, very hard, definitely the machinability can be a bigger problem. For example, this is titanium alloy. The titanium alloy is very, very hard, and also the heat transfer. This is the thermal conductivity property is very, very poor. I told you, and we machined the titanium alloy on the lathes, and finally the workpiece caught fire. Okay, because the heat cannot be conducted efficiently. So this is a bigger problem. However, EDM can do it very, very easily. And so here is regardless of hardness or whether it is hardened steel, tungsten carbide, or special alloys for aerospace applications, for example. And no matter how hard this material is, as long as it is conducting, electrically conducting, I can use EDM and to machine. So this is a very, very amazing one. And also you should also know that this EDM is a non-contact process. Why is it non-contact? EDM experience no or very small mechanical stress on the machine surface compared to the mechanical stress experienced in conventional manufacturing processes due to cutting force. Our traditional machining.
Sounds like a good class.
Yeah. Nolan, what do you say? You hear what?
Yeah, I heard it too.
Huh?
I don't know what he said.
Okay. I know that. What do you say, Nolan?
I don't think he can hear us.
Oh, do
Are you muted maybe?
No, I'm muted. Yes. I'm muted also, I think.
Yeah, it was Nolan.
Okay. So let's continue. So this is a non-contact process EDM. The complex, in addition, no rotation of workpiece or tool is necessary, and the machine has have a very, very high autonomy. So the complex cutting geometry, the sharp angles, the internal corners can be machined with precise accuracy. So this is very, very beautiful and acceptable and surface finish. On the other hand, so this is advantages. Okay, so you should know. Okay, if I ask you what is the advantage of EDM over the traditional one, and what is the limitations are, and you should be able to come here and to tell me. So the limitations are relatively low material removal rate, MRR. MRR stands for the material and removal rate. You should know that, okay? This acronym MRR stands for material removal rate. So this is surface modification of machine surface, and so this is the weather layer and heater affected zones. So this is surface finish because of high heat, unlimited size of workpiece and tool, for example. And here are the advantages, disadvantages. So disadvantages include low material removal rate, and this weather layer and heater affected zone. Weather layer and heat affected zone results from the high heat, right? And the limited size of workpiece and tool. The workpiece and tool cannot be very, very huge. So this is the three disadvantages. Everything has advantages and everything has disadvantages. So this is a historical root of EDM and despite to the discovery electrical discharge. So here is a history. I want you guys to look at this one. And then we talk about here, okay? So this is, although EDM process has found widespread application in industry over the last 70 years, and true macro EDM came to exist first in 1968. So this is a micro EDM. Micro EDM, you should know micro EDM. We have micro machining. Micro EDM means that the features we are going to EDM is at the micron scale. So this is demonstrated the first application of micro EDM by drilling a minute hole in 50 micron, a silicon carbide plate. Since then, a significant amount of research efforts has been focused on development of EDM and micro EDM. So Dr. Zheng is the EDM expert and also the micro EDM expert. So here is the history. This is the background of this is the EDM. And you should know what is EDM, what is EDM, and what is the advantage of EDM, what is the disadvantage of EDM, and also what is the micro EDM. And then we talk about the principle of EDM process. So this physically speaking, and what is EDM. So we look at this is a picture. This so we have this picture here. So here, and this is the principle of EDM process showing the gap phenomena and the respective the voltage and current waveforms. So here we talk about this physics. EDM means that we have electrode and also the workpiece. And if this is electrode is wired and to the power is powered, if the electrode is moved toward the workpiece, okay, so then they will arc, and the arc will there will be the arc. The arc will generate a lot of heat. Right? So EDM is a process of machining electrically. So this electrically, you need to power it. Conductive material. So this is must be conductive material. And interestingly, and Dr. Zheng and I published a paper recently and talking about how to EDM the non-conductive materials. I'm going to show that paper. So how to do that is we do some trick here. By precisely control the sparks that occur between the electrode, you must have electrode and the workpiece in the presence of the dielectrical fluid. So you must have the electrical fluid. And what is the function of the electrical fluid? And the electrical fluid is used to flush away the debris. Okay, flush away the debris, and you just generate and using the arc of the EDM. And in this process, a potential electrical potential is applied between electrical conductive electrode and workpiece material. The gap between these two guys is maintained between the tool and the workpiece. So a charged electrode is brought toward the oppositely charged workpiece and by the servo mechanism. So this is the space workpiece. Okay. The electrical field is the strongest at the point where the distance between the electrode and workpiece is least. So if you are interested, and you can look at the reference one, as the number of ionic particles increases, the insulating property of the dielectrical fluid begin to decrease along a narrow channel centered in the strongest part of the field. A current is established as the dielectrical fluid becomes less of an insulator. So then the heat builds up rapidly as current increases and the high thermal energy vaporizes some of the fluid, workpiece, and electrode. Also, the discharge channel begins to form between the electrode and workpiece. Such intense localized heat flux, and leads to extreme instantaneous confined rise in temperature, which would be in excess of 10,000 degrees C. The 10,000 degrees C can almost melt anything we know, right? So that's the reason the EDM can be used to machine almost all the materials we have now. the high thermal energy vaporizes the electrical fluid, workpiece, and electrode. The high thermal energy also, as the discharge channel becomes broader between the electrode and the workpiece. Toward the end of the pulse duration, this pulse, it will always have, I'm going to talk about this pulse. As the current and the voltage have stabilized, and the heater and pressure within the vapor bubble have reached their maximum, and some metal is being removed. So because of heat. At the beginning of the pulse interval, there's a pulse, right? We have a pulse. The current and voltage drop to 0 at the very beginning of the pulse interval. Within one pulse, another pulse, between the pulses, and we have an interval. So as the interval, current and voltage drop to 0. So the temperature decreases rapidly, okay, after the pulse is gone, and collapsing the vapor bubble and causing the molten metal to be expelled from the workpiece. And finally, the crater. We can have craters. If we look at the EDM arc by arc, for each arc, we have a crater. So the crater is formed by the implosion of the vapor bubble. The expelled metal solidifies into tiny sphere and dispersed in the dielectric, which will be flushed away by the dielectric. That's the reason I tell you, dielectric fluid is very, very important to flush away the melt material. The solidifies after the material melts, if the temperature goes down, and so this molten material will be solidifying as a sphere. The volume removed by single spark, the arc, is small in the range of so small. But this basic process is repeated typically 10,000 times per second. So this is very, very quickly. The frequency is very, very high. 10,000 times per second. That's 10,000 hertz. Just after a discharge, the next discharge depends upon the distribution of debris in the gap and the generally random surface irregularities. After discharge, the gap will have debris, gas bubbles, and the tar, which is raised from the disintegration hydrocarbon dielectrical fluid. If the sufficient time is allowed for deionization of the dielectric fluid, the flushing is adequate. The occurrence of the next discharge is random in time and space. Otherwise, the concentration of debris and ions in the region of the preceding discharge is likely to propagate further discharge in the same region. So the process mechanism of the EM and the related voltage and current responses over time is shown in figure 16.1. So I'm going to show 16.1. Okay, so here, this is the voltage. We have the voltage between the electrode and the workpiece. And here is the current here. Current here also. Here is the time. As the time goes from here to here, we have voltage. We will also have the current. So you can see the first one, and I say this workpiece, and this is the electrode. Show the gap phenomena and respective the voltage and current is a waveform. The first one is a pre-breakdown, the pre-breakdown of the electrical material. The voltage applied between electrode and workpiece. So the voltage is applied. The second one is a breakdown. The electrical breakdown creates plasma channel. So this one, plasma channel. And we have both, this is the voltage and also the current. We will have a plasma channel. And the third one, the discharge. And we will have the discharge, heating, melting, evaporation of the material will happen. And the fourth one is end of the discharge. The fourth one, plasma inclusion and removal of molten material here. And the last one, the fifth, will be post-discharge. You can see, and here will be a crater. Also, solidifying and flushing of the debris. So this is the dark points here, and the stand for the solidifying of this debris and from the molten material. Right, so here is 1, 2, 3, 4. The 4 stages. So this is as one pulse. At another pulse, this is interval. At another pulse, if when another pulse is coming, and we will have the second crater if it is not repeated at the same location. Any questions so far? Is if I give you and this picture, I want you guys to tell me for each of these stages and tell me what happens, and you should be able to do that, right? Right? Okay, here's the pulse. There's a pulse. And usually the pulse, a pulse, we have V, also have I. This is one pulse. And then we have interval. Another pulse, another pulse. Usually the frequency is 10,000 hertz, 10,000 times per second. So this is the frequency is very, very high. You should know, okay? So use your own language. If I give you this picture, but I remove what these captions here. What I want you guys to know to do is explain using your own language. Actually, I don't want you guys just and print the screen and crop this caption and then paste this caption here. Right? You can do it if you want, but what I want you to do is use your own language and to show me what this is 5 pictures. Show us. So there are several the series have been proposed and to explain the complex phenomena of erosive spot. So named as follows. I want you to know this one also, even though many of you guys will not conduct research, pursue a career in this EDM. But if you know this one, I think it will be like you very, very much. Yep. First one is electromechanical theory and thermomechanical theory, and this is thermoelectrical theory. So this is references. So the electromechanical theory suggests that the abrasion of material particles takes place as a result of concentrated electrical field. So this is from this perspective. So this theory proposes that the electrical field separates the material particles of the workpiece as it exceeds the force of the cohesion in the lattice of the material. So this theory neglects any thermal effect. Experimental evidence lacks the support for this theory. So experimental evidence lacks support for this theory, does not support the theory very well. So on the other hand, the second theory, thermomechanical theory, suggests that material removal in EDM operation is attributed to the melting of the material caused by flame jets. So these so-called flame jets are formed as a result of various electrical effects of discharge. So, however, the shortcoming of this theory is that this theory does not agree with experimental data and fails to give a reasonable explanation of the effect of spark erosion. So this is the shortcoming of the second the theory. But finally, the thermoelectrical theory, the best supported by experimental evidence, and suggests that metal removal in EDM operations takes place as a result of generation of extremely high temperature generated by high intensity of the discharge current. Although well supported, this theory cannot be considered as definite and complete because of difficulty in interpretation. So these are 3 theories. Okay, 3 theories And which theory is best one? Why? Why this theory is not good enough? So I want you guys to know that as engineering students, experimental results are the most important thing. If your theory, if your model cannot match the experimental results, and you should not blame the experimental results, right? Understand it? And you should consider your theory means something, or your model means something, because the experimental results are always true. Facts, that's facts. That's how it works. But if your model cannot, if your simulation results cannot match the experimental results very well, that means and your model means something. Experimental results should not be blamed. And then we talk about the EDM system components. So I want you guys to know, okay? Definitely this problem will appear in our panel. Because this is conceptual, and also you can showcase your understanding of EDM when you have an interview. So when you both say, can you tell me what are the typical components in an EDM system? So this here is the result. We have because we have electrode, and we must have a pulse generator unit for discharging, and the servo system to feed the tool. The tool will be moving, okay? And the electrical reservoir and pump and circulation system, and working tank, and with cooling device, XY table accommodating the working table, and the tool holder. So graphically, here is the diagram for typical EDM system. So we have this is XY stage. So this is our workpiece. Right? So this workpiece is located in the reservoir, not reservoir, in the container. And this container has this is the electrical fluid. So here is a pump to supply the electrical fluid. And why we need a pump to continuously supply the electrical fluid? The reason is that because of high temperature, a lot of these fluids will be evaporating, and as the time goes, the amount of fluid will be decreasing within this tank, within this container. That's the reason we should have to continuously supply this is the electrical fluid. So here is the thermal control, and thermal control the movement of the tool. So this is this stage, and in this direction, this is XY, and in the horizontal plane. And here is the data acquisition system. Data acquisition system controller is a PC computer, and we have a gap detector. We have an AD converter. AD converter means the analog to digital converter. Analog to digital converter. Okay. So because the computer can only recognize this is the digital number, not a digital signal, not instead of this analog signal. So here's a pulse generator. It's a pulse generator. Usually have a pulse generator. Okay, pulse generator will control this is the supply of these pulses on this is electrode, and all this pulse generator can output to the oscilloscope for this displaying also. So here this stage is controlled by this controller as well. So here is a typical the system of the EDM. So in the final exam, I will remove all these labels and ask you guys to tell me on what they are. Any questions so far? No questions? We talk about the pulse generator or the discharging unit. And we have several different pulse generators. One is RC type. One is a transistor type. we have two different types. I'll go through very quickly. Okay, so here first one is the RC type resistance capacitance type was the first type used for EDM. It is still being used in finishing and micro machining because the conventional transistor, the pulse generator, do not produce a constant energy pulse that is sufficiently short, one very short one, because for the finishing and micro machining. So as this filter, this is RC, R is resistance, C is capacitance. So this is a straight capacitance here. So this is the tool and this workpiece. So this is 6.3. It shows the schematic representation of this RC type pulse generator. In RC, this circuit and discharge pulse duration is dominated by the capacitance of the capacitor. Is a capacitor, and the inductance of the wire connecting the capacitor to the workpiece is here. The frequency of the discharge depends upon the charging time that is decided by the resistor and used in the circuit. And therefore, R should not be made very low because arcing phenomena can occur instead of sparking. And a critical resistance is desirable, which will prevent arcing. Discharge energy is determined by the used capacitance and by the string capacitance. This is used capacitance. This is the string capacitance. That exists between the electrical feeds, tool, electrical holder, and work table, along with the work table and between the tool, electrode, and workpiece. And this means that the minimum discharge energy per pulse is determined by the string capacitance. So all the charge stored in the string capacitance is discharged until the working gap together with the charge stored in the capacitor wired to the circuit. In the final finishing, when minimum discharge energy is necessary, the capacitor is not wired and machining is conducted with the string capacitance only. Right? It can easily generate the pulses with high peak current values and short duration, as can be seen from this figure, allowing efficient and accurate material removal, and meanwhile achieving the required surface finish. Finally, the pulse conditions with shorter discharge duration and a higher peak current provides better surface openings due to smaller discharge cradle. So here is, I'm going to show you, this is the figure. Okay, so here is the ideal voltage time and current time characteristics for this is RC type. For this, A is RC type. RC type, this is the EDM system, the pulse generator, RC. You can see here is a gradually the charging voltage, and this is a breakdown voltage. And here is the current, this is the voltage, and here is the current. And here is one pulse interval, another pulse interval, another pulse. So this is RC. And then the transistor. So here is the transistor type. RC, because RC, and we usually have this kind of curve. The transistor, and we have very just like step here. So here are the advantage of RC type pulse generator and its capability of generating smaller discharge energy using string capacitance and ability to generate very short pulse duration. So this is the advantage of RC, okay? For the finish machining, And also for the micro machining, because we just need to use a small amount of energy. So this RC is an ideal way to do that. So you should know that what is advantage of RC type over this is a transistor type. So as a result, RC type pulse generator can provide controlled and accurate MRR with very good surface finish. Also, RC type pulse generator usually has an electrically low MRR because the discharge is very low. And from this low discharge frequency due to the time needed to charge the capacitor. Moreover, thermal damage can occur easily on the workpiece if the electrical strength is not covered. The electrical strength is not recovered after the previous discharge. And the current continues to flow through the same possible channel in the gap without charging the capacitor. So this is the RC type of pulse generator. So I want you to know under what condition we should use RC type and what is the advantages. The conditions are finish machining and micro machining because we just need to use a small amount of heat to generate the features. Questions? And then we talk about this is a transistor type of pulse generator. We see the graphical comparison between RC type and transistor type already. So transistor type is widely used in conventional EDM as it provides higher removal rate and due to its high discharge frequency. I want you guys to know what is the comparison between transistor type and this RC type. Okay? The pulse duration and discharge current can arbitrarily be changed depending on the machining the characteristics required. So this is the following figure. I'm going to show the following figure. 60.3. This we just talked about. 16.3b. Here. So this is the RC type. This is the transistor type. So here. So FET transistor. FET is the transistor. R is the resistance. Workpiece, the two electrodes. So this is the part. So that picture shows the representation of basic transistor pulse generator. A series of resistance and the transistors are connected in parallel between the direct current power supply and the discharge current. And the discharge current increases proportionally to the number of transistors that are switched on at the same time. The field effect transistor FET operates the switching on and off of gate control circuit. Maybe this one. Okay, I think you have learned this some materials offered by the EE, right? Electrical engineering, right? Are you guys familiar with the transistors? Capacitors,
Inductors.
but no transistor. Okay. So in our mechatronics, which is a senior course, which I already teach, and I'm going to teach you guys. This is transistors. The transistors operate the switching on and off. This gate. It's just this is a gate. This is not the traditional switch, but this is a high-tech switch. Gate control circuit. In order to generate a single pulse, the gap voltage is monitored and to detect the currents of discharge. And after preset discharge duration, the FET is switched off. However, there is a delay in signal transmission from the occurrence of discharge to the switching off of the FET due to the time constants in voltage attenuation circuit. So the pulse control circuit an insulating circuit, and the gate circuit for the FET. So this is the delay here, right? So the transistor type pulse generator can precisely control the on time and off time. This is for the pulse, and during machining, as can be understood from figure 6.4, the B. So here, it can precisely control the time. On the contrary, for the RC, you cannot. It is always a curve. It's always a curve, RC curve. The transistor type of pulse generator can generate higher discharge energy and thus able to provide higher MRR. However, it is difficult to keep the constant discharge duration shorter than several tens of nanoseconds within the transistor type pulse generator. That's the reason RC is ideal. RC type is ideal for finish machining and nano machining, or this is the micro machining. For this is transistor type, it is more general. It's ideal for the conventional one. For this is conventional one means that this is the size of the products is not very small. Okay, everyone, I'm going to stop now. And what I want you to do is that, and you should be able to find out the history of the EDM and the physical, what is the physical explanation of EDM, the principle of EDM, and what is the system components of this EDM, and what are these two typically used. This is the pulse generator. One is RC, one is transistor type. And when we compare them, and what the advantages are, what are the limitations are, right? There's no kind of calculation anymore from today. Does that run? All is conceptual. If your interviewer asks you some this is conceptual questions, and you should be able to answer. I'm going to